to prevent all interaction, you know, it's part of the fun of using this, that when you choose your restaurant, you see where it is. When you click on a location near you, you'll get to see the restaurant. So we want to put bad content on good pages, allow good interaction, and prevent bad interaction or risks. Another example here has a social networking site. Here's some piece of, I don't know why people keep telling me stuff on Facebook. I never really had time to read it. You know, somebody's waiting for the airplane and it's bad, and I don't know. That's life. But here you can, Facebook has this large collection of user-supplied applications, and they're displayed on pages. And when an application is displayed on a page, you'd like to interact with the application, but a malicious application has the potential to find out anything information on the page, my username, my friends list, and other things, or interact with other applications. So there's other place where you have user-supplied content on a trusted site, so untrusted content on a trusted site. So here's just a kind of a schematic. In the advertising case, there's a publisher. There's some information associated with a publisher site. The advertising network supplies an advertisement. The potentially bad stuff is shown alongside the good stuff. This is one where there's a login information on it, so bad advertisement could steal login information. And we'd like to constrain the actions of this bad content to keep from subverting the good site. The idea for social network sites is pretty much the same picture. Here's some attack applications we wrote and put on Facebook just to test our attacks, just to make sure, but bad content inside a good page. So that's the sort of security problem I want to talk about for the next 20, 25 minutes. How do we constrain or sandbox bad content that's shown on good sites? And there are lots of applications and reasons why that's a current problem and something worth looking at. I'll show you one example later, but we've found a fairly long series of attacks on the kind of mechanisms I'm going to talk about. The three big examples that sort of we used as motivation for this work are Facebook JavaScript, FBJS, which is the language that users write these user-supplied applications in for Facebook. Yahoo AdSafe, which is an advertising screening filter. And Google Kaha, which is a more complicated thing, but it's a Google mechanism for isolating bad content on good sites. And at least in the Facebook and AdSafe case, we found several attacks on each of those platforms who communicated with the Facebook and AdSafe teams, and they've fixed those things and so on. But this is not an easy problem to solve. There are good, smart people working hard on this in industry, and we keep finding attacks on their mechanism, which is the reason that I think that an analysis is useful. We've been able to find these attacks by trying to prove their absence. And this is a good example of theoretical work, like programming language analysis, programming language techniques, having an application of finding practical attacks on very widely used current sites. I think Facebook has 200 million distinct users on any given week. So these are widely used sites. So the Facebook setup is Facebook applications can be served in two ways. One is integrated on the page, and that's the case that's interesting. They're written in a subset of JavaScript called FBJS, or Facebook JavaScript. It follows the kind of pattern I showed on the picture before. It goes through the Facebook server. It can be filtered and rewritten, and then it's served to Facebook users on their site. Their goals are to contain the actions of these applications so they don't access the document object model, the data in your browser. They don't change the Facebook execution environment, and they don't change the libraries that are used by other applications. So there's a basic site integrity and confidentiality issues here. And their basic approach is to eliminate certain things from the code that runs on Facebook user sites to keep it from doing certain bad things. So here's one of my collaborators, Sergio's page, with a kind of a pop-up of what it looks like internally. All of this data is available in the data structure associated with displaying this page. And a malicious application that could escape the FBJS sandbox would have access to that information, and that's what we're trying to protect here. So JavaScript as a programming language is a particularly serious challenge. So one of the most basic things we looked at when we started looking at this is, what would it take to be able to rename variables consistently in JavaScript programs? So if you took any other reasonable programming language, or let's say any reasonable programming language whatsoever, it's a kind of basic thing that if you rename a variable where it's declared and then rename all uses of it, you get something that's the same program. Those two things parse to the same parse tree because the variable names go away at some point in compilation. You get the same thing happening. This is not at all true in JavaScript. And one of the first things we try to do is figure out what's the largest kind of most reasonable subset of JavaScript where you can rename variables. Another thing is, what properties of objects are accessed by the program? Also very, very hard thing. If I give you a Java program and said, what methods are called on objects in this class, you can find out right away. JavaScript, completely open-ended problem. So very difficult language from a static analysis point of view. But static analysis is basically the perspective of the Facebook site when it takes a user-supplied application, is going to send it off to some Facebook user. It doesn't get to stand there and watch it run. It has to do some processing on the code before it sends it. And so this is a traditional programming language static analysis problem with all of the security consequences I've mentioned. So what are some of the things that make JavaScript difficult? Well, all kinds of things. There's this prototype mechanism so that parts of an object can be defined not where the object is defined, but someplace else in its prototype. The way that methods on objects are defined and added to objects, removed from objects, redefined, makes predicting the way a program goes complicated. Then most programming languages, there's a notion of runtime stack and the place where local variables are defined. That's separate from other data areas. In JavaScript, you can have an object that happens to be some part of your stack and access it just like other objects. Complicated. You can convert strings into code. You can eval as a function that takes some text and then turns it into a program instruction and runs it. So very hard to predict what eval is going to do unless you can figure out what the value of some string operations is going to be. There are also these implicitly called functions that appear nowhere in the text of your code but get called all the time. So there are cases where some expression requires a string. How does the evaluation process produce a string? It calls a toString method on one of the objects. Where is toString? Well, it's up in some prototype somewhere. If somebody was able to redefine the toString method for objects, you would change the way every program executes. You could cause the program to do whatever you wanted. So difficult context. We have good security reasons to want to solve these problems. Challenge. So some slides may get a little bit technical, but that's my job, do technical stuff. I want to kind of show you some of the challenges and the technical nature of the work, and then as well as its applications. Seems fitting for the occasion. So what we started with is working with an informal standard for the way JavaScript behaves. It's an ECMA standard for what is a subset of the JavaScript that's implemented on most standard browsers. But since we're looking at what's a good safe subset of JavaScript that could be used in Facebook and other things, a subset is fine. What we're looking for is a safe subset. Facebook only supports a subset of JavaScript close to what's standardized here. And so it's fine to focus on a subset of the full language for this particular application. And it's hard to believe, well, a year